I think we start to get critical mass here amongst the participants, and it's 8 p.m. GMT. So welcome everybody to our already traditional webinar series on vector symbolic architectures and hyperdimensional computing. And my name is Evgeny Osipov. So today we have the last webinar of the spring session, or the midnight sun session, so to say. So we have two exciting talks, both of them somehow related to natural language processing, but the second one is very is about hardware implementation. So it highlights the importance of the practical importance of VSA and HD computing, and shows the potential. So I hope you enjoyed the talk. So the first talk will be given by Hob Quiroz. So please, Hob, I'm muting myself.
Yes, thank you. Well, hello, everyone. So my name is Hob Quiroz, and I'm a PhD student from Mexico, from the National Polytechnic Institute. And in this session, I'm going to share some of the ideas and results that we have been working on in relation to vector symbolic architectures and hyperdimensional computing. So my advisors, Professor Ricardo Barron and Marco Ramirez. Okay, so for many natural language processing applications, estimating similarity and relating between words is a key task, because they serve as the basis for classification and generalization. Once you have a numeric value to distinguish between two words, two entities, you can more easily classify them. Nowadays, the vector space model, or also called distributional semantic models, are playing a leading role in natural language. And these models are based on the distributional hypothesis of meaning, which roughly states that words with similar meaning tend to occur in similar contexts. Before moving on, it is important to note that even though they are often used interchangeably, similarity and relatedness refer to different things. A commonly cited example to explain this difference is the following. Cars and gasoline would seem more closely related than, say, car and bicycle. But the latter pair are certainly more similar. This was by Resnick. So in this first image, for example, we can see a small text, and we can see how gasoline and car appear in several parts together. And in this other, which is an extract from the Wordnik ontology, we can see how bicycle and car share some classes. So for example, they are both physical objects, and they both have wheels, and they are transport. So similarity and relatedness are very close concepts, and most PCMs can measure both. For example, Word2Vec can give us a good score for gasoline and car, which makes sense, and also a good score for bicycle and car. However, and in general, these distributed models lean more toward estimating relatedness, just by the way they are constructed. In this work, I'm going to take the definition of semantic similarity proposed by Tversky, which says that pair similarity increases with its commonality and decreases with its differences. In other words, the semantic similarity between two concepts depends on the degree of correspondence between its semantic features. For instance, car and bicycle, they both share taxonomic features, function, and material. It is important to know that when Tversky talks about this similarity, he talks about general concepts in general. So this can be applied to images, sounds, etc., not just words. But I'm going to use this definition to work with words. So each concept, word, can be seen as a set of features. And to know how similar the concept A and the concept B are, we can see how many semantic features they share and how many semantic features they are different in. So we have developed a concept representation model based on a vector symbolic architecture, in which the semantic similarity depends on the degree of correspondence between the semantic features. I'm not going to describe the properties of high-dimensional spaces because most of us are aware of them. I'm only going to mention that I'm using some binary vectors, the binary scatter codes framework, where the dimensionality of the vector is 10,000, and I have implemented addition, multiplication, permutation operation, and I have a Hamming distance as the metric, and of course I have a memory. So in this model, the most important concept is what I call the concept vectors, which are defined as the sum of the multiplication between the several relations and with several features. I'm going to put an example later, but this is more or less this is the equation. And this idea it has been proposed before. For example, with Gallant, we can also see this concept in some of the Plate's book, in Canerva's article. So at this first stage in our work, we wanted to use this equation, but we wanted to use the most relevant features. So that is a hard problem, but we start with that question. And the thing is that semantic features are completely subjective, and they have to be obtained from humans, and preferably from many humans. And we use the semantic feature dataset, which is called the McRae dataset, which was developed specifically to extract semantic features from humans of more than 500 concrete concepts. Each concept is associated with between 15 and 25 features, and it's more or less like this example. We have knife. It has several semantic features. This is going to be what I call the relation, has, made of, etc. And this is going to be the feature itself, handle, still. And we basically create the representation of knife by multiplying, dividing, splitting this feature by the relation, has, and by the feature value, handle. And the interesting thing is we also have how frequent the people mention these features when they try to describe knife, and the class, the type of feature. The advantages is, well, this was a dataset very clean, very easy to work with, and it has a diversity of features, as you can see. And the problem, of course, is the limited size. 500 concepts is really is very few concepts, really. And the other thing is that this dataset was mostly used in cognitive science and not much in computer science. So we couldn't really compare with several works. And we actually have to create an evaluation set to evaluate, to know how our performance. So we selected 64 concept pairs, and we asked 35 human subjects to rate how similar these concepts are on a scale from 1 to 10. So, for example, we can see the most similar concepts are shoes and boots, spoon and fork, really similar concepts. We are only working here with concrete objects. We're not using abstract concepts or imaginary concepts. Okay, for each pair of concepts that we use, we've computed the semantic similarity with our model. The McRae, the dataset, they also provided with some similarity measure. However, that similarity measure they provide was not coming from humans. The only thing that was coming from humans were the features. The similarity value was estimated by them. And we also use some distributional models and some WordNet-based methods. We had good results. We knew that this was a very almost a toy example, not a toy, but almost a toy example. We have a high correlation value. But the most important thing for us in this was that the McRae dataset, that is the similarity measures that they get, we were slightly better than them. And these two, our model and the McRae datasets, they were using the same features. So the only difference between this one and this one was that we were using vector representations. Okay, so the next step was then to scale. So we choose ConceptNet, which is a freely available semantic network designed to help computers understand the meanings of words that people use. Giant semantic network. This network uses information from several sources like dictionary, OpenSeek, Game with Purpose, even WordNet. A lot of information is from WordNet. And well, here we have large amount of words, a diversity of features. So for example, here we have camera is the relation capable of, part of, has a, is a lot of semantic information. And this is a concept that is a project that is still growing. It is active. Some of the disadvantages that we're going to see are they have redundant information. A lot of information is repeated multiple times. We need to access via web API, which can be a very slow process. We have to consult some of the features from the web, and it also needs preprocessing. This is the structure of the nodes. So, for example, here we can see a starting node, which are going to be the concepts we want to create representation of. So Apple, we have an ending node, which is going to be the feature, eating. We have a link between them, which has a label, for example, used for, and a weight. Usually the weights are between 1 and 2, and the higher the weight, the more relevant the feature is. For example, this union is going to say that an apple is used for eating, and this has a considerable weight. We can also see that some information in ConceptNet is that an apple is related to Newton, and this, of course, has a weight, a much smaller weight. We want to extract several features that are the most relevant. So we have one issue, which is a lot of information is redundant. So in the previous approach, we take the relation used for, this relation was assigned random vectors, and we had also the features itself. Each of these features was assigned a random vector, and then we multiply and create the representation for the concept. However, as we can see here, this is a purse. If you look in Google, this is what appears, and a bag, this is what appears. Of course, bag here is a more general concept, but we can see that if we put attention, none of these features appears exactly the same in these features. So if all of these have random vectors, and all of these have random vectors, when I compare purse with bag, for the relation used for, they are not going to share any features. However, we are, in common sense, we know that carrying money or carry things should be more or less similar to carry things and carrying groceries. So we have a problem there. And well, we couldn't, if we assign only random vectors, we're going to have features all over the place, and we cannot really encode concepts properly. We can also use some lemmatization. which is useful. For example, all of the words starting with carry, all the phrases, so are going to group together. However, we still want hold and to be close to carrying, because in this context they mean very similar. They have very similar meaning. So this was not enough, and the solution was to use a conventional DSM to cluster the features first, and then map each feature to a binary space. For example, purs and back have both several relations, is a, used for, has, etc. I'm going to focus only on used for. These are some of the features associated to that relation. Is purs used for carrying money, etc. Okay, so I'm using a conventional DSM, which is number batch. Number batch was created by the same people by the same research group of ConceptNet. It is based on Word2Vec, and they just modify some information using knowledge and some things from ConceptNet. So in number batch, or we can see this in Word2Vec, all of these phrases as such are more or less together. So these are the ones about carrying. For example, a purse can be used to look good in the case of women, and the bag can be used for do exercise. You can put a lot of weight and lift. So in this space, which is 300 dimension, the real numbers, we can start to do some clustering, hierarchical clustering. So we can group together all of these, and all of the other features that are different. We can also group them, and then we can map to a binary space. So the way we map to a binary space is we take the point or the phrase, the feature that is in the center or the method of this cluster, the point which in average has the smaller distance. We assign to this point a random vector, okay, carry things a random vector. But then to the other things that are more or less similar to this, we assign some vectors that are close to this first point. So these are not random. We select a parameter to know, okay, I want this to be, I don't know, 100 bits away. So I take randomly 100 bits, I change 1 to 0 or 0 to 1, and then I have a structure like this. Okay, I do that for the other clusters as well. Looks good, and exercise. So all of the central points are going to be almost orthogonal between them. So this is more or less like the other approach. But each of these vectors, the surrounding points, are more or less also be approximately orthogonal between. So once I have the features in this space, then I can encode the concepts by the equation. So I can encourse purs for used for and select all of the features I'm interested in. And of course, this has to be done for all the other relations as well. Okay, so we wanted to also, we don't want to use our own evaluation set. So we use the Symbolic 999 dataset, which was developed in 2015, and it's a dataset specifically produced to estimate a genuine similarity between pairs of words. So they use this example, for example, for a coast and a shore. In this dataset, they have a high similarity value, and they compare to WordSim, which is supposedly also a similarity dataset, and it has a high value. these both are more or less are synonyms, but we also have clothes and closet. So in this case, for Symbolic, they have a very low value because clothes, in essence, is different from a closet. This is furniture, and this is an object that you wear. And in the case of this other dataset, this has a higher score. So distributed models generally have reached a low scores on Symbolic. The best results are always coming from hybrid models. So hybrid, I mean that they combine distributional information and knowledge. Here I have some of the results. I have here the pair numbers from 0. I'm only using the Symbolic noun subset. And so I'm only using 666 of the total words of this dataset. And here in this is the Symbolic 999 and all the crosses as from my models. I put this image because I have to mention that some of these outliers, for example, this and this and this, they are antonym words. So in Symbolic, antonym words are considered dissimilar. For example, this point here is the pair top and bottom. So top and bottom are antonyms and they have a very low score in Symbolic. However, by the way I'm defining similarity, top and bottom are actually pretty close because they are both direction, they serve to locate, etc. And also these words over here, they are outliers because they are antonyms. And this is where are we in the state of the art. So these are some of distributional models, some knowledge-based word models, and we match the inter-annotator agreement of for the Symbolic. So this parameter that the dataset provides, we match it. And we also, as in the previous approach, we have a slightly better performance than the vector space model. This vector space model was the base in which we constructed our representation. So we have a slightly better performance. We are still a bit close from the best performing model, which is this by Reksky. And they also use a hybrid system. They combine information from distributional as well as knowledge information. Okay, now this idea of mapping a structure from one space to another, it was very interesting to us and is currently being applied in another task, which is the summarization of text. I'm not going to get into details, but basically, this is a task of 2002. It was a contest, and they gave you, you have an event, something happens, and you have several news from the same event, which are a bunch of text. I have divided my analysis in the part of speech. So I separate nouns, adverbs, adjectives, verbs. And for each of these part of a speech, I perform in using Word2Vec. In this case, using Word2Vec, I find some groups. So, and for each of these group, I map each word to a binary space in which, in this binary space, these points are no longer features. They are words per se. And so for using these points, these words in the binary space, then I encode the sentences as the sum of words. For example, John plays with a dog. I remove the stop words and things like that. So I add John, dog plays, dog. So in this approach, I'm not using knowledge. I'm just using this mapping. So I take the structure of Word2Vec, and I map that more or less to another space, a binary space in which I can do more interesting things. Once I have all the sentences encoding of this text, I select the more relevant sentences. I'm not going to get into details, but basically, you also do another cluster of sentences, and the biggest cluster, the bigger clusters are the most relevant, we say, and from these biggest clusters, we extract the most important sentences. We are having good results so far. It's still work in progress. Well, this is my final slide. Some of the contributions we have had is that we designed a representation model to estimate similarity following Tversky tutorial approach. This model employs a VCA framework which allows us to use the properties of high-dimensional spaces, for example, the tendency to orthogonality, to model semantic spaces. We have, of course, this representation can be interpretable. We can not only say that a chair or a knife are similar by a number, we can say they are similar because they share these features. We can also customize these representations. We can say, okay, I don't want to know about taxonomic relations. I just want to encode from ConceptNet all these all the information about what a concept has, what an object is used for. We can customize more or less the representation. And finally, this idea of, we use the idea of using a conventional vector space model to assist us to construct a high-dimensional binary representation. And this mapping is currently being used in other problems, such as the summarization. Okay, that was my presentation. I have to say it's a great pleasure to participate in this seminar, and thank you very much.
Thank you Hope very much for this excellent presentation. So we have a couple of minutes for questions. Please, if you have any, unmute yourself and speak loud.
So is relation and semantic similarity pretty much the same thing as syntagmatic and paradigmatic relations in linguistics?
Yes, actually, one of the papers that is supporting the Symbolic 999 is that they find that the paradigmatic definition of similarity was better for using Symbolic. They also detected that, for example, in the case of antonym words, it is better to use a paradigmatic definition of similarity. So in the case of Symbolic, they consider synonyms and antonyms dissimilar, but in a paradigmatic relation, they are going to be similar. So yes, I think about your question, yes, we are closer to be working with a paradigmatic relation.
Any more questions? Maybe one more and then we take the rest offline.
Yeah, Job, very interesting talk. One thing I was curious about was you were creating a feature space there to have similarity structure, and it looks like you did that in a pretty manual way. You were describing how you started sort of with a uniform distribution, but then clustered them to have the similarity you wanted. I was wondering why you did that rather than use a feature space that was derived from some sort of distributional semantics.
Okay, thank you. I think you referred to this part.
Yeah, exactly.
Okay. Yes, if at first, well, the first experiments were, of course, a bit manual, but I didn't say that here we have two parameters, because, of course, the distribution between these points, these new points that I'm adding, at first I was doing it like, okay, 100, bits away and then see what's happened. But that is actually is going to be a parameter of the model. So in this model, we have two parameters that we have to tune. We have to iterate to see, okay, at which first, this is the first parameter, at which point these features are close enough. This is one first parameter which we have to iterate. And then, okay, how in this new space, how far they are going to be from the center point. So we didn't want to use like we could use probably here more information to say, okay, according to this, these new points have to be to this distance. But we, instead of that, we just iterate. So for this problem, we have the like an objective functions, which is to increase, to maximize the Spearman correlation. So we just iterate this parameter, how big these groups are, and how close and how far the points in this space are going to be. Yeah, probably we can use some another information to say, okay, this have to be arranged in this way. Yeah, we can do that.
Yeah. Okay. Yeah. Okay. Okay. Yeah, I understand. So it was like you were varying the intergroup, the intergroup sort of radius compared with the between group radius.
Yes. Yes.
Yeah.
Yes.
So how sensitive were your results to that parameter variation?
Okay, it was, for example, in this, as you can see here, in both cases, I was expecting to have like pretty close to a mean. For example, between the distance between this center and this center is approximately 5,000. So I think, okay, these are going to be probably 500 or I don't know. But I think that the model works best when these points are actually at a high, more or less high distance, which is 4,000. This means this point, this is not at scale at all. This point and these points are at about 5,000, but this and these are at 4,000. And this was the best result. From here, just varying, it wasn't so sensitive. This was more or less stable. But yes, I was surprised. I was expecting to have here like closest distance, but if we look like the distribution, the normal distribution for this type of representation, 4,000 bits away are still considered pretty close.
Okay. Okay. Interesting. Thanks.
Thank you.
All right, I feel like I have to interfere here, so we are a couple of minutes behind. So let's leave all possible other questions for offline discussion using our mailing list. So thank you very much, Hope, for your presentation and all participants for the questions. So